Hello everyone. In this video, we will begin to examine topic 7.2 nuclear reactions, and in particular, we will begin to consider the relationship between mass and energy. Now, we've seen mass before, or the concept of mass before. When we first ran into mass, we preliminarily defined it as the amount of matter, or amount of stuff. That captures our basic intuitions about what mass is and sort of how it works, and is not a bad working definition for a lot of science and a lot of physics. But since then, we've actually seen two more precise definitions, the connection between which is up to this point a complete mystery. And it's been a little bit subtle because we introduced the idea of mass sort of slowly and in different contexts. But it is actually important to sort of look back a little bit and see how the two other definitions that we've introduced are related and why they're completely distinct. So the first is the idea of inertial mass, related to that idea of inertia. And that's just the measure of a body's resistance to acceleration. So we can think of this mass, m, as being defined as the ratio between the net force and the acceleration on an object. So if you double the net force and measure the acceleration, that relationship will be constant, and that value is known as its mass. That's what's known as the inertial mass. And related to the property of inertia. But we've also seen a different concept that we have also called mass, and that's the gravitational mass. And what the gravitational mass is a measure of a body's sensitivity to gravitational fields. That is, if you increase the gravitational field strength for the same mass, you will get an increased force known as the weight on that mass. And to see that these are completely different ideas, completely separate, which turn out to be the same number, and that's an important idea here. These are two different ideas that, as far as we know, are exactly the same value, which is a little bit strange. Compare the way that electric fields work on charges to the way that gravitational fields work on masses. So in the case of an electric field, if you had a random charged particle in the electric field, it would accelerate in the direction of the electric field, feeling a force, F, equal to Q times E, the electric field. That force would then cause the mass to accelerate. And so that force would then be equal to ma, and you could solve this for the acceleration if you wanted, in order to find the acceleration for a given mass. Notice here that how the force is calculated depends on the charge, otherwise known as the sensitivity to the electric field, times the electric field, giving you that total force. And then that is equal to the inertial mass, the resistance to acceleration, times the acceleration. Okay, so notice how this works. But in the case of gravitational fields, right, something that we saw way back in topic 2 is actually a little bit of a mystery. Notice that the same argument applies here. There's a property of an object that measures its sensitivity to the gravitational field, but that property we called mass rather than charge or anything else. That mass, the sensitivity to the gravitational field, how much of a gravitational force it feels, is the gravitational mass, mg. And so conceptually, just like QE is equal to m sub I times A, well, the gravitational mass times the gravitational field is equal to the inertial mass times the acceleration. Now, because those two numbers are the same, we then cancel them out, and we say in free fall, the acceleration of an object is equal to the gravitational field strength. This is sort of fundamentally related to me being very picky about the units of gravitational field being newtons per kilogram, and us calling 9.8 the gravitational field strength rather than the acceleration due to gravity in free fall. Because although g is equal to a, if those two are, or if the object is in free fall, they're conceptually different things. This is the gravitational field, this is the acceleration. That is more obvious in the case of the electric field. E is obviously not A, and Q, the charge, is obviously not the inertial mass. As it turns out, these are two conceptually different masses. So, what gives? That is, what is the relationship between them? How come they happen to be the same value? Right? That seems to be an utter mystery. To fill that in, we need help from our boy Einstein. And we'll talk about what he had to say in the next video.